Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our applied linear algebra series, and today we're going to be talking about dimensions of subspace as well as inner products or dot products. So in the previous lecture, we introduced what is a vector space, right? Okay, sometimes the OneNote is buggy. So we introduced a formal definition of a vector space. And we say that a subspace V in RD and how that is similar to being a subset. So those two are somehow interchangeable. Now, what does that mean? It means that all the vectors there in that subspace V are closed under addition and scalar multiplication. So when we add two vectors or when we multiply some vector in that subspace V, the resulting vector that we get out of it is still in that same subspace. That's what it means to be closed, right? What else did we say? Or what else did we cover last time? We said that a set of vectors, let's do V1 all the way to Vn. We say that the set is a basis for V, and we have two criteria for it, right? One is if the set is linearly independent and they span that subspace V. So that's what we said, right? Those were the two criteria. Okay. So now let's actually go into the topic for today. We're going to talk about dimensions of subspace and dot products. So here's a theorem for you. So theorem 4.1. Okay, let's consider a subspace, call it V, and this is a subset in RD, and a set of vectors. So we have a subspace and a set of vectors, V1 to Vn, that span the subspace V. I forgot to add the word basis. So meaning they are linearly independent and they span that subspace V. That means, okay, not that means. Then any vector, say we have a new vector W, and that's also in that subspace V, can be written as this. W is summation, a linear combination of the Vj, right? So W can be written as a linear combination of the basis vectors that we have. Okay. And here we say for a unique set of vectors, or I mean scalars, we're going to have a unique set of scalars, meaning no two scalars are similar to each other. And so when we do that, and we manage to get a linear combination, then those scalars are basically the basis coefficients. I'm going to write that down. These scalars are, okay, let's wait for this to load. I feel like I know why it's loading a while, because I put so many in the same file. So I'm going to switch over to the next one after this. So these scalars are what we call the basis coefficients of W. All right. Now, how do we compute these basis coefficients or these alphas? Well, we have a couple of ways of doing it, right? So for one, we're gonna write the whole thing, right? So we do alpha 1, v1, all the way to alpha n vn, and that's just equal to W. And here we see that, well, say we have this Vj, that's just Vj1 all the way to Vjd. Okay? And then this W, we can actually see this as W1 all the way to Wd, because they're all in Rd. Okay? And so the way this works, since we already know what that is, we can actually write it this way. Alpha 1, 1, V1, V1, 1, alpha 1, 2, V1, 2, and we keep going. Or shoot, 2, 1, my bad. 2, 1. Keep going. Alpha 1, N 1. And this is loading. This is equal to, I think, W1. And then we just keep going from here. So alpha 1. Oh no. So these are, okay, let me just, I can't open OneNote for some reason. That's funny. Why can't I open OneNote? I can open this. Oh, there you go. My bad. There's just one. There's just two. And 1, 2, 1. Okay, and then here we have 1, 2. Alpha 2, 2, 2. Alpha n, N2. W2. And we can see a pattern here, right? So do alpha 1. Then I believe this one's V1, I guess D. And we keep adding it, alpha 2, V2D, all the way to alpha alpha D N D, if that makes sense. N2. Yeah, yeah. Okay, cool. Okay, so we have that is equal to WD. Right, so what are these exactly? How many equations do we have? Well, here we have D equations. How many unknowns per equation? N unknowns, right? How many scalars do we have per equation? That's n equations. Or how many scalars? N scalars, not n equations. Okay, now we have a proof here. So here's how the proof's gonna go. I'm gonna prove theorem 4.1. So, okay. So yeah, OneNote is a bit buggy as of the moment. Wonder why. So by definition, of a basis, we already know that any W in the subspace V can be written as a linear combination of the basis vectors. So by definition of the basis, we actually did this 2 times. We know that any W vector that belongs in the subspace V can be written as a linear combination of vectors, basis vectors. So actually, I can't go in OneNote. Can go into any app, actually. Okay. So the only thing we need to do, we need to check uniqueness. Ay, ay, ay. Yeah, okay. This one's a bit buggy, so I have to move to a different page for the next lecture. Yeah, because I'm not sure if you guys are looking at it or if you guys can see it, but apparently OneNote is not responding. And I'm guessing because there's too much stuff here. Anyway, going back, we only actually need to check the uniqueness of the basis coefficients. Are they the same? Are they different? We actually want them to be different. Okay, there's a couple of stuff here, so let me just... So we're actually going to do a proof by contradiction. So towards a contradiction, we assume that W can be written using two sets of basis coefficients. Okay, so this guy here, W, even switch to the pen. Is it? I think OneNote's bugging me. Goodness gracious. Okay. Do I just switch for the proof? Actually, I'm gonna finish this. Actually, I'll just switch it to the next. Like, we'll see if that works. Let's see. It's loading. Uh-oh. Ay, ay, ay. This thing's not responding. It's weird. Oh, there you go. Somehow I managed to get that part. Oh, there you go. Nice. Okay, let me go down here. Keep going. Okay. So what I'm gonna do, I'm gonna cut this whole thing. It's loading. But it's not cutting. Let me make a new. Okay, this is funny. You can't copy your content right now. If I right click this thing. Ay, ay, ay. Okay. Oh, there we go. Nice. So I'm gonna do, so I'm gonna make a new page. I'm gonna put here. There we go. Now this should work fine. I'll just put like midterm review too. Doesn't even matter what I put. Right, much cleaner. I think OneNote can only store a specific amount of text per paper, so I have to be mindful of that. So we assume W can be written using two sets of basis coefficients, okay? Ah, there we go, much cleaner. So we could have different basis coefficients. That's our assumption. So we can say W can be written using some scalars from alpha, right? Oh shoot, that was a V. Keep going all the way to N. But then alpha could be written using some beta. Right? So what we're gonna do is we're gonna subtract. I'm gonna say W minus W is equal to 0, which is the same thing as me subtracting alpha 1 minus beta 1, V, and I keep going to N, alpha N, beta N. And then here we see that we actually have some sort of linear combination happening. Alpha 1 minus beta 1 all the way to alpha n minus beta n. That's actually, those are just scalars. So it's kind of like a linear combination. And apparently when we do all of these scalar multiplications and vector addition, we're going to get a 0. Now, since the VJs, because it says that they are a basis, the set is a basis, or they are basis vectors. So we know that they are linearly independent and they span the subspace V. So we know they're linearly independent. So what does that mean? We can use our alternate definition, right? So this means that this equation only has trivial solution. The alternate definition states that if there's only the trivial solution where all the scalars are 0, beta 1, I'll do 2, it's fine. Alpha n minus beta n. Now those are just 0. And what does that mean? So alpha j is actually just beta j. And this is a contradiction. Because now we know that the basis of these two are not unique. They're the same thing. So apparently alpha j and beta j, all the scalars are the same thing. Okay. So in general, when we have a subspace that's in RD, or part of our RD, this subspace can have infinite choices of basis vectors. So there is an infinite amount of possibilities, but there's a big, however, big but, the number of basis vectors there are lots of choices, but the number that we can have for each choice turns out to be the same. And so based off of this, this allows us to define the dimension of our subspace, which is what our topic is for today. Okay. So let's do it. Let's now define the thing, right? That's what we want. Here's the key part. The number of basis vectors, so the number of vectors that we have, is somehow related to the dimension of the subspace. Just like how the number of components of our vector is related to the dimension of the vector, right? So let me just do it. So here is the actual definition of this thing. So we say that for a subspace, say V in Rd, so that's how you write it. The dimension of our subspace here is it. Here it is the number of basis vectors that span V. So the dimension of our subspace V is the number of basis vectors that span V. Another way of saying it is the dimension of our subspace V is equal to n, where n, if the set V1 to Vn is linearly independent. They are linearly independent. That set of vectors then that's the number, it's the dimension of the subspace V. Okay, actually, I think these are two different meanings, huh? Now that I think about it. Because here it says the first statement, dimension is the number of basis vectors that span V. Oh, okay. So for it to be a basis, it needs to span V and it needs to be linearly independent, right? So it's basically just the number of basis vectors. That's it. And these basis vectors are linearly independent, or the set of these vectors is linearly independent. And this set of vectors also span the subspace V. And so that's the number of basis vectors. Cool. Okay. So somehow they're kind of related. So, so we have the set is linearly independent. I'll add something. And so this one is kind of relating it to the first one, but the span of this set from V1 to N is actually just the subspace V. Okay. Let's do an example here, or a couple of examples. So let's try, what's the dimension of our subspace R3? Well, the dimension is 3, right? Since the span of, let's say we have our standard basis vectors. So these are basis vectors. And so they are linearly independent. And so they span R3. And so they are a basis. And there are 3. The number of basis vectors are 3. And so the dimension is 3. Okay. Okay, let's keep doing something else here. About, let's consider, I don't know, subspace V is the span of these vectors here. 1, 0, 0, and 0, 1, 0. What in the world is this? What is the dimension of V? The dimension of V is, so again, we look, are these linearly independent? No. Hmm. A way I could check actually, which is kind of funny, is just put these up and put one of them down. So I could just do 210 000. Oh shoot, I actually can't do that. Uh-oh. Yeah. I could divide this by a half. 1.5. 0. 1/2. I think this was -1. I could put this back. 212. 210, I mean. And then this one would be 000. So now it's in echelon form. Here we see there are no pivots in every column. So these are not, this set is dependent. So if this set is dependent, that means we can write one of them as a linear combination of the other. And so definitely the dimension is not 3, right? Because that's not what's in our definition. So we're asking for, so they don't span V. Wait, do they span V? I forgot to check. Do they have a pivot every row? They don't. They have a pivot every column? They don't. So they don't span R3. And they're not an independent set. So there's only one thing to check. What are the number of basis vectors? How do we say they're basis? We need to check if a vector is linearly independent. So that's one. Another idea is, yeah, if they span something. So actually, based off of this idea, we could look at, take this out. And so from there, what do we have? Now we have two linearly independent vectors. Why is that? Because there's a pivot in every column and there's a pivot every row. So they actually span R2. And so if they span R2, so they span that subspace R2, and they are linearly independent. So the number of basis vectors is 2. So we have two vectors that are linearly independent. They span R2. So the dimension is 2. Okay. And we can actually just pick any of these. 2 of the 3. Actually, it could be any of them, to be honest. It will work. So I'm just gonna say maybe I would pick the basic one. I would just do this. The span of that is R2, which is a line, pretty much. Okay, great. Now, try something else here. Let's consider, okay, we have a lot of exercises. So this subspace, we go with V again, is the span of, say, vector 1, 1, 1, negative 1, 2, 3, and 3, 3, 3. Immediately we can see this is a dependent set. Why? Because we can write the third vector as a linear combination of the first one. And so from here, we are definitely going to check out that they do not span R3. Okay? Are they linearly independent? These two are not, right? They're the same thing. So what is the dimension of this guy? I could check. I could put them in an augment. I could put them in a matrix, not necessarily augmented. I could do that. But an easier way, I think, would be to just check out one of them and then just go with this. And then we see from there. So I could just do, okay, what does this do? Yeah, I could just do this. 1 minus 1, 2 minus 3. I could do that. 1 minus 1. You do this. 8 of 3, 8 of 1, 8 of 1. Let me check this one. So I would just, I would multiply this by 3. And I would have the same thing. I would multiply this by a positive 3. And I should get this guy. And from here we can see that they are linearly independent because there's a pivot in every column. But there's no pivot in every row, so they don't span R3. In fact, here, if we take out this row, they actually span R2. So this guy here spans a line. If they span a line, R2, the number of linearly independent vectors, oh yeah, the number of pivots in every column is also 2. So the dimension is 2, right? So there's that way of checking. I could just do this. The span of this is G, or in this case, R2. Same idea. Did I write that out? I did. All right. Yeah, this was not shown in the lecture. I'm just writing it out. This is conceptual algebra, linear algebra. We're done. Those are the examples. So just a quick note of checking spans. So here's the idea. This was not in the lecture. I'm just going to point it out. So when given span of set of vectors, to find dimension of that subspace that's apparently equal to the span, when that V is equal to the span, need two things. One, check if set is independent, dependent. Look at pivot every column. Okay. Another thing we check for row. Check if they span Rn if the set is V1. Oh no, shoot. They span Rd, not Rn. If we have some Vj from V1 all the way to D. How do I check? Look at pivot every row. Okay. And what does this mean? It means that the number of linearly independent vectors, which is the number of pivots every column, is actually just going to be the dimension. Okay. Here we can see that It's actually just pivot every column is equal to pivot every row, or actually sometimes it's not equal. Number of independent vectors is equal to that dimension. Okay, just a quick note. This is not in the lecture or anything. It's just a thing that works. Okay, when working with RD, there is very often a special basis that is natural and useful. So let me just put that out here. So when we're working with RD, there's a special basis. I think we know what that is. We just haven't seen it in this form yet. That is natural and useful. And so these are the vectors. RD, uh-oh, e to the j. Now what is e to the j? Or not e to the j, e sub j. E stands for standard basis. And this is actually just equal to, well, ej1, ej2, ejd. Okay? So these are standard basis vectors. We're just generalizing them instead of xyz. So j, k. They could only be two things. They could be 1 or a 0. 0 or 1. 0 if k is not j. And of course, if k is j, they're 1. Okay? Right, let's see. So maybe an example would be easier. When we do e sub 1, this is 1, 0, all the way to 0. E sub 2. This is 0, 1, 0, and all the way to 0. See the pattern? E sub 3. This is 0, 0, 1, 0. So it's basically the third position that's a 1, the second position that's a 2, that's a 1, and the first position that's a 1. So here it's the when j is equal to k, if we're being mathematically precise here. Yeah, we're just doing indices here, but that's the idea. So, okay, there's a nice way that, okay, this one's nice. The professor put this. So I'm going to put it here. So simply put, all entries of EJ are 0, except jth entry. Okay? And that jth entry is going to be a 1. That's what that is, right? And we have a name for it. So these are called the standard basis of RD. Okay? So I guess we can do an example. So what is the standard basis? Okay, this one we're going back to calculus 3, but we're going to frame it differently. Or not really differently. We're going to frame it in a linear algebra way. So standard basis for R2 is what? So this one we've probably seen. It's the ij, right? This is e to the 1, which is just 1, 0. And we also have e to the 2, 0, 1, right? We have two components in that vector. How about for R4? Have we seen this? E to the 1 is 1, 0, 0, 0. E to the 2 is 0, 1, 0, 0. E to the 3 is 0, 0, 1, 0. E to the 4 is 0, 0, 0, 1. Okay? Now it is easy. Check that these vectors are linearly independent, because they are. And they span RD, because they do. And at the same time, okay, this is where the nice thing happens. So I'm just going to point it out. So these vectors are linearly independent and span RD, wherever that may be, right? Because they're a basis. So of course they're linearly independent. See how like we're kind of mixing up the ideas together? So at the same time, any vector, say V, and we say that's in RD, a d-dimensional vector can be written as the following. So they can be written as, say we have that V, here would be the components, V sub 1 to D, which is the same thing as this. V1, V to the 1, V2, okay, V to the 2. We keep going to VD, E to the D, and we can write it in summation. It doesn't really matter. Do a J. Right? All of this is still V. That same V vector. That's what's so nice about standard basis vectors. We can do this kind of linear combination and we'd still get the same thing. Okay. Right. Let's switch gears here. So we're gonna observe something geometrically. So in 2D, how does this look like? How does E sub 1 look like? Like that, right? And this has the vector 1, 0. Or another way you could write it is in column. Then we also have E to the 2, which is the same thing as 0, 1. Right? Now in 3D, how would this look like? Well, in 3D, we have E to the 1. We have E to the 2. And we have E to the 3. Okay? Then, oh wait, I forgot to add. These are all 90 degrees. 90, 90, 90. There you go. Now, Here's a question. And I think we've seen this in Calculus 3. If not, I could refresh your memory. Have you heard of this term? Can we make sense of, here's the term, orthogonal? Basically means they're 90-degree angles. They make 90-degree angles. Orthogonal is the same thing as perpendicular. Now, if you ask me, why do we use orthogonal instead of perpendicular? I don't know. Fancy word, but it's the same thing. Or right angles. So can we make sense of these angles in RD? Is there some sort of relationship that we can find between these angles and an RD? Is there a way? No, no. Well, actually, there is. I think we've discussed this in our calculus series, but I'm also going to refresh my memory. I don't know. I forgot. But I know there was a way to do it. And we call it the inner product. We used to call it dot product in the calc series. If you guys can watch my video, I haven't seen that video in a while, so I forgot. But we might talk about this idea again, but in a more abstract way, I would say. But let's see. Let's see what we can do here. So, okay. Let me let me do my best. Anyway, so for any pair, so we have a pair of vectors. So we have u, v, and we say they're in RD. So they're d-dimensional vectors. We're going to define their inner product. Now, what does it mean to do an inner product of two vectors again? Or we formerly called it dot product, if we remember from calculus. Let's do an example. So say we have, okay, I'll do this in a calculus way. We have v. We have, let's say, 1, 2, 3. Then we have u. Let's say this is 4, 5, 6. I don't know why I picked the most stupid thing here. So the dot product, right? We do a dot was when we just add, we multiply each of their components and we add as we go. See how all of that falls into place? 28 plus 4, 32, I believe. And we end up with a scalar or a number, right? So that's how the dot product worked for us in Calculus 3, if you've seen my calculus series. Here, we're going to talk about it in a more abstract way. You probably have seen, I'm going to throw you off. You've seen this. You seen that? That's the dot product or inner product. So we remember how we used to think of everything here as a column vector? Transposing it, that's what T is for. U transpose is basically turning it into a row. And there is a reason why we do that. So this is the same thing as turning it into a row. There's a reason why we do that. And it might not be clear yet, but the way we actually organize our values here is extremely helpful. Right? That's what it means to transpose one of them. Cool. And that idea is the same thing as the dot product of this. And this is the same thing. You've probably seen this one. I know, I've seen this one. And this is the same thing as summation all the way to D from j equals 1, uj, vj. Okay, that's weird. Someone put I. Why did they do that? So these are all equivalent notations. Now, these are basically the same thing. So whenever you go to a textbook, you see one of these notations, you know it's the inner or dot. All right, let's do an example here. I'm going to use one of them. I could play around with it if I want, but let's try this. So we have that vector. We have this vector. How do I get the dot product? So we do 1 times 4. Oh, I already did that. We got 32. Easy, right? Let's do, I'm kidding. I'm not gonna do another one. So this inner product. So what about inner product? How do we actually interpret this? So actually, this one I haven't really touched up too much in my Calculus 3 class. But apparently there are some useful properties here that I haven't discovered yet, if that makes sense. So that number 32 is actually very meaningful. You can use that to do more nice mathematics with other things. So we'll check that out. I know I've seen a couple. So we can use that number to provide very useful and important properties that we're gonna go over here. So here's one of them. One is symmetry when we're doing a dot product. What do I mean by symmetry? I mean, if we do the dot product of u and v, that's the same thing as doing the dot product of v and u. It's the same thing. And this goes for all u and v in RD. Okay? You've seen this notation, so I'm going to use it. I'm going to keep using it. 2, we have linearity. What do I mean by linearity? Well, when we have u, and then we have scalar alpha, v plus w. Well, wait, that's confusing. How do we do a dot product of that one? Well, this one's a bit tricky, but actually this is the same thing as, and there's a way to prove this. I think I'm going to prove this later. This is alpha times the dot product of u and v. So we multiply this thing first, plus u and w. Okay. And we say that all u, v, and w are in RD. And alpha is a scalar in this case. Okay? We're going to prove this later. Let's do the third property, which is positivity. So here's the thing about dot products that I find interesting. If we multiply, or if we do a dot product of the same vector, it's always going to be positive or 0. Okay? It's always going to be that. And then if we do another property here, definiteness. So definiteness is just, say we have u, we have another u. This is equal to 0 if and only if u is 0. So if we get the dot product of two zero vectors, that's going to be a 0. Okay, let's quickly check. I'm kind of excited to go to that second one because I think that one's very confusing. But we're going to prove all of them anyway because we want to lay the foundations, you know? So let's quickly check. Based on what we know in the previous ideas, how can we check if these properties are true, right? Start with number one. So we're saying that this is symmetry, right? So this is the same thing as a summation to D. Then this goes from J to 1, U sub I, V sub I, not I, I say I, meant J. And actually we've seen this idea, but this is the same thing as V sub J, U sub J. And that is the same thing as V and U. Right? So for real numbers, these are true. I don't have to spell it out. Okay, number two, okay, this one's pretty interesting. This one is interesting. We have U alpha V plus W. How do we prove the idea? Well, okay, I guess we can start with doing a linear combination. So we go all the way to D, right? We do a U sub J, and then we multiply that idea with alpha V sub J plus W sub J. Now what do we have? We can actually distribute the U to both sides. So how that would look like is alpha, it could be any actually, alpha uj vj plus uj wj. Interesting, right? We could do that. We're just distributing the stuff. We distributed, so we multiplied this u value to here and to here. And so we get that operation, we get that term after. And then what happens next? What do we think? Well, now we can we can split them actually. And we can take out the alpha as we do that. So we do this, which is just what? uj vj plus this guy, uj wj. And then what do we have? Pretty close. Alpha u. Oh, look at that. These two are the same thing as alpha u v plus u w. Very cool. That one's really nice. See that? Summation. So this is linearity. That's how this thing is true. But if we ever get confused, then we can just prove it again. Right? Because in the test, I don't have a cheat sheet, so I'll probably just prove it again. We'll see. We'll see. Okay. Now we have, here's this other one. U. And here, apparently this is always greater than or equal to 0. How do we prove that? Well, you could do this. This one is easily a proof because we're always squaring it. So it's never going to be a 0. or it's never going to be a negative value in this case. Okay, let's keep going. I hope I'm not getting you bogged down with the notation, even though it looks scary. But it really isn't. It's about just explaining how things work, you know? Okay, let's try this last one. Hmm. If and only if u is zero. So we say this u, and suppose they are zero, right? Then this is just zero when we do a summation here. Yeah, I mean, this one's pretty self-explanatory. When we square everything, that just a zero, since all actually it's just zero anyways, right? The problem, yeah, it could be greater than zero, but since I mean everything's just zero, I would just say it's zero. I wouldn't even put the greater sign. It's just putting the greater sign because of the squared, but I wouldn't really, yeah, I wouldn't really put it. Yeah. So this equality here can, okay, I'm just gonna finish the proof. Can hold if u sub j is indeed zero, and conversely, if u is equal to the zero vector, then well, their dot product is basically zero. So actually, we did talk about this in calculus. If their dot product is zero, what does that mean? It means they make a 90-degree angle. That's one of the relations of the dot product. Anyway, so based off of this, we already notice something interesting, right? What do we notice? I'll tell you. Or if you know, you know. But if we take the dot product and we take a square root of that, that's the same thing as doing it in summation, right? Square j. And that's the same thing as the norm of that u vector, or the magnitude, right? So we did talk about magnitude in, I forgot which one, lecture 2, I think. I forgot. So what does that mean? The square root of the inner product is just the norm. Okay, I'm gonna write that out. So similar to the norm, there are other ways we can define inner product. So that's one relation, right? I haven't talked about the angle. But one relation that we can do with inner products is if we square them, or we we put an exponent, we put them to the power of a half, that's gonna give us the magnitude of that vector, right? And there are many other ways we can define inner products, and all of those inner products will induce a norm as well, right? Okay, let me show one. Actually, I don't need to write this. Yeah, I'm not gonna write this one. It's okay. So now that we have an inner product, we can make sense of angles and orthogonality. So this is one way, right? So squaring inner product of two, I should have just continued with that, of two equal vectors give gives the magnitude of that vector. Okay, right. What else? What else? What else? What else? So now that we have an inner product, we can make sense of angles and orthogonality. And we're going to use that using inner product. Although it's the hardest to interpret, but it's there. Angles and orthogonality. So let's do a definition here. Let's try. So we say two vectors. Let's do typical U and V. They are d-dimensional vectors. We say they are orthogonal, and this is something we also did in calculus, if their dot product is a 0. So that's the relation of inner product to orthogonality. And when we say orthogonal, when we say the two vectors are orthogonal to each other, that means that this U and this V, they make a 90-degree angle. Or by half radians, I think. Might be wrong. No, I'm right. Yeah, by half. Okay, let's do an example. This one's pretty easy. I think we've seen this. I'm going to do a standard basis. So we say we have that vector, 1, 0, and 0, 1. So these are orthogonal, right? How do we know? If we take the dot product of these two standard basis vectors, we would get 0. 1 times 0 is 0, plus 0 times 1 is 0. So that's one simple example. Let's do another one. We say that, oh, actually, this one's another fact. I wouldn't say example, but a fact. But the professor put this as an example. We say that any pair of standard coordinate vectors, I'll call it basis, standard basis vectors. So this one's a more general idea, right? So we do e to the I and e to the k. That is, both are in d dimensions. For, let's say, I not k, are orthogonal. We're saying that mathematically this is how it would look like using that notation. When we sum it up, we'll do a j e to the, so this is how we write it, e to the ij and e to the kj. This is a 0. If I is not k. So if they're the same vector, that would be their magnitude. That wouldn't tell us anything about orthogonality. It would actually be 0, their angle, if it's the same vector. That's that's the intuition, right? I mean, if you're given a vector 1, 0, you're given a vector 1, 0, 1, 0. You're given another vector 1, 0. What's the angle? 0. If you're given a standard basis, say, yeah, that previous one, the 1, 0, and 0, 1. So if you look at this example here, 1, 0, and 0, 1, this is this vector. Uh-oh. And this vector. We say they form a 90-degree angle because their dot product is 0, or their inner product is 0. That's the intuition. Okay. Right. Let's do one more. One more. How many more do we have? Oh, that was it. This is the last one. Then we'll call it a day. So here, I'm gonna say I have this vector 1, 1, and I have another vector 1, negative 1. And we say these guys are orthogonal. Why? We can check. Nothing wrong with checking, right? This is 1 times 1 plus 1 times negative 1, 1 minus 1, 0. So they form a 90-degree angle, right? We just do a dot product. But say we have this and this vector. These are not orthogonal to each other. Now we can try. We would do 1, 1, 1, negative 2. So this would be 1 times 1 plus 1 times negative 2. This would be 1 minus 2. This is negative 1, which is not 0. So they are not orthogonal because their dot product, their inner product is not 0. And that's it. Okay, I hope you guys enjoyed this video, learned something at least. I think this was pretty cool, especially when proving and getting to the ideas. So I hope you guys enjoyed, and I'll see you all in the next video.